So hello everyone, and in this video we are going to talk about something called a maximal interval of existence. Okay, so what does it mean? So essentially, let us consider this system. Consider the system. Okay, so we are back to a nonlinear system. X prime equals to f of x, and x acting at the point some t naught, let's say, is x naught. Clear? T naught can be 0 also, it doesn't matter. T naught is some number in R essentially. Yeah? So T is, now the thing is this, what do we know by Picard's existence and uniqueness? Okay, so Picard existence and uniqueness theorem, which we have already proved. Existence and uniqueness, this is important. Okay, uniqueness showed that, let's call this system as one admits, okay, a unique solution. Where is the solution unique? It's not in the whole interval, right, but in some neighborhood of t naught. So unique solution, let's call that solution to be x, okay, of t in this interval, t naught minus epsilon, t naught plus epsilon, for some epsilon greater than 0, provided, you remember what is the, this is not valid for any capital F, right, provided capital F is in C1. Okay, so if capital F is continuously differentiable, this is true. Okay, now there are different type of questions which arise here. Okay, so the first thing is this. See, the thing is functions, let's say it is defined on different intervals here. Okay, now we'll have different solutions out of it. Yes, but how do you know that they are like same or they are distinct? Clear? That is what we need to understand first. So for this we are going to start with some lemma. Okay, the first lemma is this: let x1 x2 be solutions of 1 such that a x1 is continuous on open A beta closed and satisfies x prime equals to capital F of x on alpha beta, and also x2 is continuous, let's say on some interval beta and gamma, okay, and satisfies x prime equals to f of x on beta gamma. So you see, what we are saying is this: you have two different solutions on two different intervals. Clear? Now the thing is, let us put some conditions. What happens at the end point of the interval? So basically at the point beta. So let us assume that x1 at the point beta equals to x2 at the point beta, and if this common value, okay, belongs to the domain of f, has to be, otherwise f of x won't be defined, right, to the domain of capital F, then if one defines capital X of t to be x1 of t and x2 of t. When is it x1 of t? If alpha less than t less than equals beta, if t lies between beta and gamma. It's not less than equal, it is just less than. Okay, Now this x of t yields a solution, so that will actually give you a solution of x prime equals to f of x on the combined interval, so in the whole interval, okay, on the interval alpha gamma. So you understood what is this first lemma says? First lemma says that essentially you have two solutions, two different solutions in two intervals. Now the thing is this, can you combine those two solutions to get another solution? Yes. And this lemma says that of course you can. Yes. Now the problem thing is this, to prove this thing, x of t, if it is in this interval, it is x2 of t, and it is given x2 of t solves this problem. Solution of, let's put it this way, x prime equals to f of x without the data, right? Without the data. And so you see t between beta and gamma less than equal gamma, x of t is nothing but x2 of t, and x2 of t is given to be a solution. So it is not a problem. Okay. Now again, t between alpha and less than alpha and beta not equals to beta. Okay. See, at t equals to beta, if you leave that part out, then between alpha and beta, x is nothing but x1. Again, x1 is given to be a solution. So in these two part of the interval, except t equals to beta, this is a solution. That is no issue there. The only issue which can happen is at t equals to beta. Clear? Now what you need to do is, first of all, at t equals to beta, we have this condition x1t equals to x2 of t. Clear? What you need to show is that actually gives you a solution. How do you find something like this? So essentially you just calculate what happens to this problem, x prime at the point t, which is beta, equals to, so you just have to show that this is true. Okay, x prime at the point beta is equals to f at the point x of beta. How do you do it? Here you use the definition of limit, definition of derivative, okay, of derivative. So you use that definition, and using x1 beta equals to x2 beta, you can actually show that this is true. Yes, and then once this is true, then of course it actually solves the problem. So what we are saying is this, you can actually plug, okay, two solutions together, and the only condition which you need is at the point where you are plugging those two together, both the functions should have the same value. Once that is there, then you can do that, plug, you can add the two solutions in such a way that you actually can have a solution over the whole interval. Yes. So I want you to check this part. Please do this yourself. So do it yourself. This you have to check it yourself. Right. With that in mind, what we are going to do is we are going to look at some more theorem. So another small lemma which we are going to write down, and this I really don't think I need to prove it for you, because you can handle this thing. So what we can do is this. Let's say let a compact set K, subset of omega, subset of Rn, and where K is compact, right? Where K is compact, and what is omega? Omega is open. So what we are doing is we are putting a compact set inside a open set. What we are saying is, then there exists a larger compact set, and what is it? Let's call it K prime, which is again contained in omega, and a delta positive. Clear? Such that for every x in K, okay, the closed ball, what is the closed ball? It is given by Bx delta bar is contained in K prime. Is this okay? It is not a very difficult thing to see. So please do it yourself. Again, check it yourself, do it yourself. So what am I saying? I am saying that let us assume that you have a open set omega. It is in Rn. And now I have a compact set K. Some compact set K which is inside omega. What we are saying is this. Then you take any point x in K. Here you can find a delta, and please remember this delta is independent of x in K, right? This holds for any x in K, okay? So you can find the delta such that the closed ball with the center at x and radius delta is always contained in another compact set K prime, which is again contained in omega. Yes. So how do you find that the delta which you are going to get is uniform? That you can use your definition of compactness. So please check this yourself. Okay. With this we are going to do something called a uniqueness theorem. Okay. In a certain sense, uniqueness. So let's look at that. Uniqueness theorem. Right. Before we do that, again, let me again refresh you why we are doing this thing. What we want to do is this. Picard's existence and uniqueness says that you will, as long as f is continuously differentiable, you will get an epsilon such that t naught minus an epsilon, t naught plus epsilon, there is a unique solution. Now the question is this: how much can you stretch that interval? Is it possible to stretch it further? That is the question. Or is there an interval which is like a maximum interval? So after that it is not possible to extend the solution anymore. Picard's theorem will give you a solution. Now the thing is, it may be possible to extend it. The question is, how much can we extend it, or is it possible? Yeah, that is the question. Okay. So for that we are going to do a uniqueness theorem first. So let suppose f from omega subset of Rn to R is locally Lipschitz. Okay, and let you have two solutions, x1 and x2, be the solution of 1. What is 1? 1 is x prime equals to f of x, and x at the point t naught is x naught. Now is defined. So essentially what we are saying is this: let's say that those two solutions, yes, they are defined for alpha j less than t less than beta j. Clear? J equals to 1 and 2. So what I am saying is this. See, it's a initial value problem. So whatever solution we are getting is in a neighborhood of t naught. So see, here the initial value is t naught, right? We need to find a curve which passes through t naught, and at the point t naught it should achieve the vector x naught. So what we are saying is, between t naught minus epsilon and t naught plus epsilon, there is a x naught. There is a solution. Now the thing is this: let's say that we are saying that you can somehow, let's say by some calculation or something else, you have two solutions which are defined in some neighborhood of t naught. The first neighborhood is given by alpha 1 beta 1, the second neighborhood is given by alpha 2 beta 2. Clear? Then what we can say is, then for all t such that maximum of alpha 1 alpha 2 and less than t less than minimum of alpha 1 beta 1 beta 2 beta 1 beta 2 where both the solutions exist, both the solutions exist or are defined, what do we have? x1 of t has to be equals to x2 of t. So this is a very, very intuitive theorem, right? See, let's say that alpha 1 beta 1, x1 is defined in here, yes, and x2 is defined in, let's say, alpha 2 and beta 2. Yes, somehow you have found it, we don't know how, but you have this information that there are two solutions. x1 is on alpha 1 beta 1 and x2 is in alpha 2 beta 2, and for just for the sake of understanding, let's just assume that this is your 0, and our initial data is given at 0. So for now, let's just assume that t naught is 0. It doesn't have to be, but let's just assume it just for understanding better. Okay, now what happens is, see, the uniqueness theorem guarantees, right? Local ellipsis functions, no problem, uniqueness theorem holds. So the uniqueness theorem guarantees that there is a unique solution in some neighborhood. Clear? Okay. And the thing is, let's say that if it may happen that you can find an epsilon here, minus epsilon and plus epsilon, okay, and in that neighborhood, of course, the two solution has to be same, right? Because of the uniqueness. Yes, but the thing is, it may happen that your minus epsilon plus epsilon, which you are going to get from Picard's theorem, may be here. So let's say minus epsilon here and plus epsilon here. It may happen. We don't know. Okay, because we don't know what is alpha 1, alpha 2, beta 1, beta 2. We don't know all that. So, but the thing is, this theorem says that you can actually up till beta 1, beta 2, minimum of beta 1, beta 2, and till maximum of alpha 1, alpha 2, you can actually stretch the solution. So basically, there will be only one solution. x1 and x2 will be same in this thing, right? Of course, it has to be because of the uniqueness. Okay, so this is what we need to prove now. Now, again, this is very, very intuitive. Clear? Okay, so but how to prove this? The proof is again, if you remember the proof of uniqueness theorem, generally we use Grunwald, and we'll do it here also, no exceptions. So again, what I am doing is I am going to take t naught to be 0 here. Okay? So we assume t naught to be 0. It doesn't have to be. This makes our life easier, hence we are doing it. And we show the result for t positive. Is this clear? For the positive time. For negative time also we can do exactly the same sort of thing. No issues here. Now, what we are going to do is we are going to use Grunwald. So we define this new function g of t to be x1 of t minus x2 of t. Remember, if we have to show x1 is equals to x2, this we did for uniqueness also when we proved Picard's existence and uniqueness. We just looked at the norm of this x1 minus x2. If you can show that g is identically equals to 0, then that will actually imply that x1 and x2 are basically the same. Now, how do you show something like that? Yeah, let's just understand that. So now you see what happens to x1 of t minus x2 of t. x1 and x2 both satisfies the equation. So it also satisfies the integral equation, and hence this is nothing but 0 to t f of x1 of s minus f of x2 of s ds. This is what we have. So, and this is valid for 0 t less than minimum of beta 1, beta 2. Clear? Please understand this. The two solutions are defined up till, one is defined up till beta 1, another one is defined up till beta 2. Clear? So the integral equation, if you look at the corresponding integral equation, one will be defined up till beta 1 and another will be defined up till beta 2. Clear? So if we combine those two together, then this t here, this will be, I can stretch it up till the minimum of beta 1, beta 2. Yes? Okay. Now, if that is true, then now you see, therefore, g of t is the norm of x1t minus x2 of t, which is bounded by 0 to t f of x1 of s minus f of x2 of s ds. Is this fine? Well, now we restrict t between 0 and t for now, where this capital T is less than minimum of beta 1 and beta 2. So in this interval, all of g of t is defined, is no issues there. And you see, this interval is compact. So x1 of 0t and x2 of 0t has to be compact. So that will imply that their union is compact. I hope this is clear. Why is it true? x1 and x2 are solutions. They are continuous function. Compact image of continuous functions are going to be compact. Union of two compact set is compact. So this is compact. Is this okay? Therefore, what do we have is, in this interval, you can find a Lipschitz constant L, right? So because of this compactness, norm of f of x1 of s minus f of x2 of s. See, f is locally Lipschitz, right? But in this compact set, any local Lipschitz function on a compact set is going to be Lipschitz continuous. So you can actually bound it by the Lipschitz constant L times norm of x1 of s minus x2 of s. Here, which is nothing but L of g of s. Therefore, if we substitute it, you see g of t is bounded by L times integral 0 to t g of s ds. Is this okay? Now, what does Gronwall say? Gronwall will give us that g of t has to be identically equals to 0. There is no other way here. For 0 t capital T. Yes. Why? Because you see that from Gronwall we get that, since from Gronwall lemma will imply g of t has to be less than equal 0 for all t between 0 t, and again g of t is negative, non-negative, sorry, g of t is, see, is norm of something, so it is non-negative, so it has to be identically equals to 0. Yes, and that will imply x1 of t has to be equals to x2 of t. Clear? Okay, and since this t is arbitrary, you see this t is arbitrary, so this holds for all t between 0 and minimum of beta 1, beta 2. Is this okay? Since t is arbitrary. I hope this is clear. This is not particularly difficult, so it can be easily understood. Fine. So what did we learn? We learned that if you have two solutions, so first theorem which we proved is this lemma. If you have two solutions in two different intervals, you can actually combine them. Clear? Provided they agree, the two solutions agree on the the common point where they meet. Now the uniqueness theorem says that if you have two different solutions defined on two different intervals, then what happens is you can take the maximum and the minimum of those two intervals, and then for that t you can actually have this solution defined. There is a unique solution in that interval. Clear? So that is uniqueness theorem. Now what we are going to do is give you the maximum interval of existence, the result. Okay, so let's write it as a theorem. So let f from omega to Rn, omega subset of Rn, of course, yes, f is a vector field, be locally Lipschitz on omega, which is of course subset of Rn. It is locally Lipschitz, we just assume. Now given, let's say, x naught in omega. Clear? What is x naught? X naught is, you see that the initial data, that is, you see x at the point t naught is x naught, or t naught is, or x at the point 0 is x naught, whatever. So the initial data is x naught. So given x naught in omega, there exists a solution. Okay, what is the solution? This is the maximal solution, x star. Let me put it this way. There is a solution, x star. Clear? What is the speciality of this solution? This is defined between minus alpha star, beta star to omega of the initial value problem, x prime equals to f of x at the point 0 equals to x naught. Clear? That is maximal in the following sense. Maximal in the following sense. So what I am saying is this, that you will have a solution, right, which is maximal. Clear? So how is it maximal? Maximal in the sense that, number one, if another solution, okay, not number one, let me put it this way, in the following sense. If another solution or function, let's say x, defined from some open interval I, open, clear, to Rn, then solves x prime equals to f of x, x0 equals to x naught. So if there is another function which solves this problem, then what will happen? This I, clear? See, what I am saying is, this is the maximum one can extend. Yes, and the thing is, since it is locally Lipschitz, you have uniqueness. So this I should always be contained in minus alpha star, beta star. And what happens in this I, that is common between x and x star? So x of t should be equals to x star of t for all t in I. This is very intuitive. So what I am saying is this, it is maximal in this sense. The solution is maximal in this sense that there is a maximal interval, clear, in which the solution is defined. And if there is any other solution, that will be defined in some open interval, right? That open interval should always be contained in that maximal interval, and both functions should, agree on this common interval. That's the important thing. Let's look at the proof. The proof is, okay, anyways, again we are going to start with just the positive one. So we will show for beta star and t greater than equal 0. Okay, now t less than equals 0 also exactly the same sort of thing happens, so you don't have to worry about it. Okay, so I'm just doing the one part. Now, we'll define a new function. What is the function? Beta star. Here, see, I have to show that there is a beta star. You see, there exists, this is the theorem. I have to show that there exists a beta star such that that happens. So, beta star, how do I get it? See, there are solutions, right, which is defined between 0 and let's say some epsilons, many epsilons. Now the thing is, what I am going to do, I want to show that that is the maximal, there is a maximal such interval. So basically I take the supremum of all such betas. So what I do is, I take the supremum of beta such that, let's call it 1. 1 is solvable for 0 less than t less than beta. That is intuitionally okay. See, between every interval between t and beta as much as we can go, okay, the maximum we can go, we just take all these betas together wherever it is solvable, and we put all these betas, we take the supremum of all these betas, and that should be beta star, right? That is how, that is what we need to show, that is what we are trying to show. Okay, now clearly beta star is positive. Why? Because of Picard's existence uniqueness. Picard's theorem. Huh? What does Picard's theorem say? There exists an epsilon such that minus epsilon plus epsilon in that interval, there is a solution, right? So epsilon is always there. I know that there is a positive epsilon such that this happens, and I am taking the supremum of all such epsilon, so that has to be positive. Now, for n equals to 1, 2, okay, you choose solutions. Choose solutions xn of 1 that exists for time t between 0 and beta star. 0 and beta n. Clear? Clear? Yes, it's fine. 0 and beta n, where beta n will converge to beta star. See, that is the supremum, so it has to converge. We are taking beta n's in such a way, so basically we are taking xn's. x1 is 0 beta 1, x2 is 0 beta 2, such a that beta n will converge to beta star. And beta star may be infinite. It may be finite, but it may be infinite also. It doesn't matter. It's okay. Now, how do you define x star? See, I have to find out that there is a solution x star. How do you define such an x star, which is defined between minus alpha star, beta star? Okay. So, to define x star, let me do it this way. To define x star, define x star given t between 0 and beta star, we choose any n such that beta n is greater than t, and let x star of t is nothing but xn of t. Clear? So for large enough, so you give me a t between 0 and beta star. Yes? So there we can always choose a n such that beta n is greater than t, because beta n converges to beta star. See, beta n converges to beta star, so we can always get a beta n which is greater than t, right? And for that t, what happens is x star, xn of beta n is defined. So xn of t is defined because xn of xn is defined between 0 and beta n, right? So xn of t is defined. I take that value and I will define as x star of t. Clear? Now you do realize that does this definition depends on n? No, it does not, because of this theorem. You see, because you see this t I can extend it, right? So because of this theorem, what I can say is this definition is independent. Definition is independent of n, right? Of n. Clear? So once that is independent of n, of course we this is the x star which you want, right? Because you can easily see that in this x star, x and x star is going to be, if there is any other solution x, then it has to be same, and in the interval has to be contained in minus alpha star beta star, 0 beta star basically, but you can do the other part. So basically minus alpha star beta star. This is okay. So this is how we show the maximum interval of existence. This is the existence of a maximum interval of existence. Is this okay? Right? So this is the case. Some remarks. As you can see by this example, by the theorem, sorry, that if there is a solution which is like a maximal in this sense, then the interval which you are going to get is also a maximal interval, right? And this interval is always going to be open. That is quite evident from this construction here, because beta star is nothing but the supremum of beta. That is how we defined it here. So remark A, please remember that the maximal interval of existence is always going to be open, is always going to be open. Is this okay? Is always going to be open interval, that is interval in R. Is it okay? Now we are going to prove another very analogous theorem, and this is very much important for extending solution to larger times. Okay, another important, let me put it this way, another important theorem which may be used to extend the solution to larger times. This is what we are going to do now. So what is this theorem? Theorem 2, let's just call it, clear? Theorem 2, and this is the theorem 1, let's just call it. Did I write any other theorem? No, I don't remember I wrote any other theorem. So this is theorem 1. This is the uniqueness theorem, existence. So this theorem is, let me put it this way, this theorem is basically the existence for the maximal interval of existence. Clear? See, the maximum interval of existence, yes, that exists. This is the theorem that says that. Here, so that is there. Now this theorem is also similar sort of the idea, but this is it may be useful to extend the solution for larger times in some cases, right? But here also I will put a red mark. Please remember this theorem. It is extremely important. It is not only here which you are going to use it, we are going to use it in future things also. So this is very, very, very important theorem. Okay, very important theorem. It does not look like, it won't look like much, but it is very, very important. Okay, let me put 6 stars there. Okay, now let's look at the theorem. What does it say? Suppose regarding the maximal solution, what is the maximal solution? The solution which we got from the earlier theorem. Regarding the maximal solution, x star, where is it defined from? Minus alpha star beta star to R n, that beta star is finite. See, here also we wrote that beta star may be infinite. Yes. So what we are assuming is that there, let's say for some problem, yes, we do not know whether we are assuming that for some problem you actually have a maximal solution between minus alpha star and beta star such that beta star is finite. Is this okay? Right. Then for any compact set, K which is contained in omega, there exists epsilon positive such that x star of t will not be contained in K for beta star minus epsilon t between beta star. Is this okay? What does it say? It says that if you have a maximal interval and the maximal interval is going to be finite, let's just say. See, I wrote it for a positive time, but you can do it for a negative time also. So basically, in that case, minus alpha star is bounded. Okay. So what I am doing is this. For now, let's just do it for a positive. So this is for positive time. Okay, that is why I took beta star to be bounded. Clear? So if you have a maximal interval, let's say such that the upper bound beta star is bounded, then for any compact set K in omega, clear? What is omega? Omega is the domain where f is defined, capital F. Yes, and what is capital F? It is this this is for the coming from that equation, right? X prime equals to f of x. Now, what this theorem says is for any compact set, doesn't really matter what compact set you choose, whatever compact set is inside omega, you can always find a epsilon such that for a epsilon, so if you are very close to beta star, that is very close to beta star, you can always find there are some element. So basically x star of t, yes, will not be contained in compact set K. So essentially what it is saying is this, that a compact set cannot contain all possible values of the maximal solution. That's what it is basically saying. You cannot put it in a compact set. Yes, but provided the maximal solution is finite. Yes, of course if it is infinite, the maximal interval is infinite, it doesn't work. But the thing is, for finite this thing is true. Okay, let's look at the proof. Again, I am telling you again and again, this is one of the most important theorem of this course. Of course, it's it's not important as it is. Essentially what happens is this theorem will be used in many different contexts. Later you will see. So the proof. See, first of all, let's say that we can say that there exists a compact set K prime, let's say compact set K prime and delta positive such that for all x in K, clear, B x delta bar is containing K prime, right? Where am I getting it? We talked about this theorem, right? If you remember, see, we talked about this lemma. I told you to do it yourself. So this is the lemma which we are using. Clear? Okay. So with this lemma, what we are going to do is this. See, we are going to take that, let M is nothing but the maximum of fx and when x is in K star, sorry, K prime, and let L be the Lipschitz constant, where on that compact set for f on K prime, on the compact set K prime, and choose, this is technical, essentially we choose epsilon positive. Okay, epsilon positive. Now you see that we claim, what is our claim? Claim is x star of t, okay, is not in K, that compact set K, if T is greater than beta minus epsilon. Clear? Of course, this epsilon here is positive, it will depend on delta. It will depend on delta positive. We'll choose such a delta epsilon. So what we are saying is this, that see, this is the epsilon where the solution exists. Okay, so you see what we are claiming is this: x star T is not in K. This is our claim for T between B star minus epsilon. So there is a epsilon such that T, if you take beta minus epsilon, okay, then sorry, beta star minus epsilon, then for all T greater than beta star minus epsilon, x star of T is not in the compact set K. Yes, so let on the contrary, suppose there is T naught greater than B star minus epsilon such that x star of T naught is in the compact set K. Okay, so then you see, if you look at this problem, y prime equals to f of y and y at the point T naught is x T naught. Yes, then this problem has a solution on T naught minus epsilon and T naught plus epsilon. Is this okay? How are we getting this solution? You remember, two things are there in two different intervals. You can just patch it up, right? Okay. So, and see, and you can say that this original solution, okay, x star, sorry, then we can say that x star, which implies that x star may be defined on 0 T naught plus epsilon open. Is this okay? See, the thing is, we are saying that let's just assume that there is a T naught, clear, such that T naught is in that compact set K, and then what we do is we take that I should take x star of T naught. See, x star of T naught is in that compact set K, right? So I am defining a new function y prime equals to f of y, and y at the point T naught is x naught of T naught. So I know that T naught minus epsilon, T naught plus epsilon, in that interval this problem has a solution. This is clear, and that solution will actually coincide with x star on the interval 0 T naught plus epsilon. Why this will happen? Because of the earlier theorem which we just proved here. So but you see, T naught plus epsilon, clear, that is greater than beta star. Clear? See, which is greater than beta star. Yes, so this contradicts the assumption that x star is beta star is maximal. So this contradicts the assumption that beta star is maximal. Yeah. So I hope this is clear. See, first of all, we are saying that if that is not true, then you can find a x star such that is always in the compact set K. Now using that x star, x star at the point T naught, that is, using that x star at the point T naught, we are defining a new function y such that y satisfies y prime equals to f of y, and y at the point T naught is x star of T naught. Here, that problem has a solution between T naught minus epsilon and T naught plus epsilon. Yes, but again x star also satisfies the exact same equation in 0 T naught plus epsilon. Is this okay? Yes, and at the point T naught, x at the point T naught is basically y at the point T naught. So what happens is x star must be y star, right, in that interval. So basically they has to be same, right? That's just you see, that's just what we proved here. The maximal, that is what maximal means. So it has to be equal. See, okay. So you see, what happens is this: if that is the case, then what we can say is that the maximal, saying that this is maximal, clear, that is actually violated. This is okay. Because you see, because x star is defined between 0 and t naught plus epsilon, but t naught plus epsilon is greater than b star. Sorry. So, of course, it happens that b star cannot be maximal, and hence the proof. So, with this we are going to end this video.